This is Kenji Fuji from Chiba Institute of Technology speaking. This time I would like to make a presentation entitled Shaking Table Test of Adjacent Building Models Considering Pounding. So let us start from introduction. What I am showing to you is a photo of damaged building in 2016 Kumamoto earthquake in the downtown of Kumamoto City. Here you see the zoom of the upper stories. You can see this part of the front building is severely damaged. As you see, the non-structural wall at the 4th and 5th stories are severely damaged. These damages are possibly caused by pounding to the adjacent building during earthquake. Such damaged buildings due to seismic pounding have been observed in previous major earthquakes such as 1985 Mexico earthquake and 2011 Christchurch earthquake and so on. So why does such pounding occur? In the downtown of the major cities, there are many buildings within a limited space. The dynamic properties of those buildings may be different due to different structure and/or number of stories. And also, the gap between adjacent buildings may be insufficient. The seismic pounding of building structures have been investigated by many researchers as shown here. During seismic pounding, the kinetic energy of each structure is drastically changed during the collision period. One structure may lose kinetic energy, while the other may gain. Energy dissipation also occurs as a result of non-elastic collisions. Therefore, the change in the kinetic energy in each structure is an important point to understand the phenomenon of seismic pounding. In this study, a shaking table test of building models was carried out to investigate the seismic pounding of low-rise buildings and a low-rise building to a mid-rise building. Based on the test results, the increment of kinetic energy during collisions is evaluated and discussed. So, I would like to explain the outline of the shaking table test. Here shows 3 building models used in the shaking table test. Two single-story models, Model 1A and Model 1B, are the models to simulate the response of low-rise buildings. The difference of two models is only the stiffness of columns. That is, Model 1A is more flexible than Model 1B, while the mass of both models are the same. 1-2-story models, Model 2 is a model to simulate the response of mid-rise building. In each building models, viscoelastic material is installed in each story with rigid support column to adjust the structural damping. The natural period of Model 1A is 0.195 seconds and that of Model 1B is 0.144 seconds. The natural period of Model 2 is 0.400 seconds for the first mode and 0.141 seconds for the second mode. Here shows the arrangement of pounding test. Because of size limitation during the shaking table test, the two building models were set in parallel. On the level 1 of each model, the pounding arm element was installed to facilitate collisions of two building models during the test. Therefore, the pounding in this test was asymmetric pounding, which caused a torsional response in both models. To minimize the torsional response, the widths of the column in each story and the distance between the two columns were determined to provide a large story torsional stiffness. The test parameters in this study is Pairing of two building models. The test 1 is a case to simulate the pounding of low-rise buildings, while the test 2 is a case to simulate the pounding of a low-rise building to a mid-rise building. And another parameter is the size of gap. The size is set to 0, 5 mm, 10 mm, and infinite. Here shows the experimental setup. The absolute acceleration of all floors and tables are measured by accelerometers, while the absolute displacement of all floors and tables are measured by laser sensors. The sampling interval is 0.001 seconds. The relative displacement of all floors are calculated as the difference of absolute displacement of each floor and that of shaking table. Here shows the stood velocity spectrum and input energy spectrum of seismic input. 3 recorded accelerations were used for the shaking table test. In this test, the peak acceleration was scaled to 40% of the acceleration due to gravity, and the time interval was scaled by half of original records. So next, I would like to explain the test results. Here shows a video of one of the tests. What I am showing to you is the time history of the test 2, which was shown in the video. Figure A is the history of the floor displacement, and figure B is the floor acceleration. As you see, sharp spikes in the acceleration response are evident when the relative displacement of Model 1B is almost equal to that of Level 1 in Model 2. A sharp spike in the acceleration response is considered here as a collision. This figure shows a normalized inter-storey drift in test 1. The normalized inter-storey drift is defined as a ratio of the peak inter-storey drift with pounding divided by that without pounding. As you see, the normalized drift of Model 1A is smaller than 1 in most cases. The normalized drift is smaller as the gap is smaller. On the contrary, the normalized drift of Model 1B is larger than 1 in most cases. This observation indicates that in case of pounding of low-rise building, the peak displacement of the shorter period building increases, while that of the lower period building decreases. In test 2, the normalized drift of Model 1B is larger than 1 in all cases. The normalized drift is larger as the gap is smaller. However, the trend of Model 2 depends on each story. That is, in the second story, the normalized drift is larger than 1 in most cases, while it is smaller than 1 in the first story in all cases. This observation indicates that in case of the pounding of a low-rise building to a mid-rise building, the story drift of low-rise building increases. In the mid-rise building, the peak story of upper story increases, while that of lower story decreases. The discussion that follows focused on the change in the kinetic energy of each structure during the collision. The increment of kinetic energy during each collision is evaluated. Here shows the definition of collision time in this study. The beginning time of collision is the time when the relative displacement between building model 1 and 2 at floor level 1 exceeds the initial gap and the relative velocity is positive. In other words, the beginning time of collision is the time when two building models began to contact, while the ending time of collision is the time when two building models began to separate. In this study, the increment of kinetic energy during collision time is calculated for each pounding for the later discussion. Here shows the sum of increment of kinetic energy in test 1. As shown here, the sum of increment of kinetic energy of model 1A is negative. This means model 1A loses kinetic energy as a result of collision. This trend is significant in the case of a smaller initial gap. And that of model 1B is also negative, except one case. Here shows the result in test 2. In test 2, the sum of increment of kinetic energy of model 1B is positive, while that of model 2 is negative in all cases. These trends are more significant in the case of a smaller initial gap. So next, I would like to show you the maximum kinetic energy in test 1. As shown here, the maximum kinetic energy of model 1A is larger than model 1B. This figure also shows that the maximum kinetic energy of model 1A is smaller in the case of a smaller initial gap. Here shows the maximum kinetic energy in test 2. As shown here, the maximum kinetic energy of model 2 is larger than model 1B. So, based on the test results, it may be concluded that the building model with more kinetic energy loses more energy due to collision and unfavorable effect of seismic pounding to the response is less significant. On the contrary, the building model with lesser kinetic energy may gain more energy from the collisions, and unfavorable effect of seismic pounding to the response is predominant. So, I would like to show you the conclusions. The main findings of these studies are as follows. The first conclusion is, in case of pounding of low-rise buildings, the peak displacement of stiffer building increases, while that of more flexible building decreases. This is obtained from the results of test 1. The second conclusion is, in case of pounding of a low-rise building to a mid-rise building, the peak displacement of low-rise building increases. In the mid-rise building, the peak inter-story drift of upper story increases, while that of lower story decreases. This is obtained from the results of test 2. The last conclusion is from the discussion on the change in the kinetic energy for each structure during collisions. The building model with more kinetic energy loses more energy due to the collisions, and the unfavorable effect of seismic pounding to the response is less significant. On the contrary, the building model with lesser kinetic energy may gain more energy from the collisions, and the unfavorable effect of seismic pounding to the response is predominant. This is the end of my presentation. Thank you very much for paying attention.